Hello everyone, this is Dr. Lennon, and we're going to be talking about the shell method today. So another way to find volumes of these objects that we create by taking two-dimensional curves and then revolving them either about the x-axis, y-axis, or even some other line is the shell method. So the shell method is nice because it's kind of just like a formula we plug things into, and we don't have to think as much about what direction we're going to be slicing things and stuff like that. So I've got the method here, copy from the book. So how does it go? Well, if we have two continuous functions with f greater than g on some interval, and we have a region bounded by two curves and two starting points, x equals a and x equals b. We could also have this with y values as well. Then we would do just like we did with a washer method and solve for x in terms of y, and then you would have your y values as your upper and lower bounds. But in general, we've just got it written in terms of x here. Then the volume you get, you basically just integrate from a to b, and you have the shell circumference, 2 pi x times the shell height, which is going to be the difference in the heights of the two functions. So really what this is it's kind of like filling up these three-dimensional objects with a bunch of cylinders. And so we'll look at some examples and see how to do that, but really the setups, there's less thinking to it, I think, than versus the washer method. So we have our first example here. We can use the shell method. We have our two curves y equals x minus x squared and y equals 0. So clearly the x minus x squared curve is always positive there, so it satisfies the first hypothesis, and the 0 function we really don't have to worry about in terms of the formula because subtracting 0 doesn't really do much. So our volume here is just given by, so we have 2 pi, the constant, and then we're integrating. The picture goes from 0 to 1 for the x values, and then we have x times the difference of the two curves, which is actually just the x minus x squared dx. And then this is a very simple integral to compute, right? We have 2 pi integral from 0 to 1 of x squared minus x cubed dx. And in fact, we can just write this as 2 pi. So then we do the antiderivative. We get x cubed over 3 minus x to the 4th over 4 from 0 to 1. And then just plug in 1. So you get a third minus a fourth. Which is going to come out to a 12th, times 2 comes out to a 6th, so this ends up just being pi over 6. So that is the answer for part A. Again, really not too much to think about, pretty easy setup and computation there. So let's go ahead and move on to another. So for the second example, we have two curves now, and clearly the parabola opening downward is on top, so that's going to be negative x squared plus 4x plus 2. And the parabola opening upward is on bottom. The curves are intersecting at 1 and 4, so we just go there. So our volume here is just going to be set up the same way. We have 2 pi times the integral. We're going from 1 to 4. And then we have our minus x squared. We have to multiply all of that by x first. Let's not forget that. And then we have to subtract everything. So we have x. And we're multiplying by minus x squared plus 4x plus 2. And then we're subtracting the bottom parabola, x squared minus 6x plus 10. So what are we getting? Let's simplify the polynomial. So 1 to 4, we have our x. What happens? Well, we have minus 2x squared now. And then 4x and 6x is going to make plus 10x. And then plus 2 and minus 10 is going to be minus 8. So again, multiply the x through, and then we'll go ahead and find the antiderivative after that. So we have minus 2x cubed plus 10x squared minus 8x dx. So this has an antiderivative of okay, so minus 2x to the 4th over 4 is actually we can cancel out, so we're going to get minus x to the 4th over 2. Then plus 10x cubed over 3, and then minus 4x squared Okay, and that's going from 1 to 4. So we want to plug in those numbers and simplify. So let's see, we're going to end up with 2 pi, and then plugging in the 4, we're going to get minus 4 to the 4th over 2 plus 10 times 4 cubed over 3 minus 4 times 4 squared, which is just 4 cubed in fact. And then we want to subtract minus 1/2 plus 10 over 3 minus 4. And we should be able to do all that in our calculator. So this comes out to 2 pi times 45 over 2, which comes out to exactly 45 pi. So again, fairly simple setup here. Just plug everything into the shell formula and it works out quite nicely. So let's go ahead and look at another example now that we have this one finished. Okay, so let's figure out what part C is going to be. Okay, so in this third example, now we've got one where we're rotating about the x-axis. So what we want to do is we want to think about everything in terms of y. So, okay, so if we think about the top of this line to where it intersects, the square root of 4 is equal to 2. So basically, we're going from y equals 0 down here up to y equals 2. So those are going to be our limits of integration. And then our top curve right here is y equals 4. And our bottom curve that we're subtracting is the arc. Now, in that one, what's going on is we have y solved for in terms of x, but we want to do it the other way. We want to write it as y squared equals x. So that's our curve. So making the adjustments now, we can do the shell method in terms of y here. So what is that going to look like? Well, our volume is going to be 2 pi, and then we're using the y limit, so we're going from 0 to 2. And instead of multiplying by x, now we multiply by y, and then we subtract our curves. So we've got 4, which is on top, minus the y squared dy, and this is what we have to integrate. So we have 2 pi times the integral from 0 to 2 of 4y minus y cubed dy. So this is just 2 pi times 2y squared minus y to the 4th over 4 from 0 to 2. So we get 2 pi times what? We're going to get 8 minus 16 over 4, which is 4. So we end up getting 8 pi as our answer here. So again, really straightforward. You just have to solve for x in terms of y and change your limits to y's. But really the process is just as simple. Okay, let's do one last one with maybe a slightly more exotic function, but really nothing too difficult here. We just have 0 and then we have our positive function over this interval. So our volume here is just given by, again, 2 pi times the integral from 0 to the square root of pi over 2 of x times cosine x squared dx. So this can be done by substitution. So the substitution is, again, we just let u be equal to x squared, and then du is 2x dx. So our integral, we can move over here. Again, we square the limits to change those over, so our limits are just going to be going from 0 to pi over 2 now. And we're going to have, we're going to have to multiply by du over 2, so the 2 is going to go away on the outside, and we just have pi, and then we have the cosine of u du. And this is going to be pi times the sine of u from pi over 2 to 0, and then integrating that, we know the integral of, or we know the sine of pi over 2 is just 1, so this integral just comes out to exactly pi. So that is it for this example, nothing too difficult. Again, once you have everything plugged in properly, you really don't even need to visualize much as long as the hypotheses are satisfied, and you can go ahead and just use the shell method. So a lot of times for finding these volumes, the shell method is the easier one to set up. But the washer method's good because it makes you think about which way to slice and how exactly you're going to go about doing that. Anyway, this is Dr. Lennon signing off.